So when I'm not teaching ERP on Mondays, and I spend my life researching solar energy. So this is really the topic that I love, and I spend all my waking hours thinking about. So Arthur asked me, and this is a new lecture by the way, so I literally wrote all of this week. Arthur asked me if I could come and talk to you about what I do and give you some sort of insight onto solar energy and its place in modern society. So this is a really practical lecture, and think of this, because this is a really small group, so think of this as a two-way discussion. So if you have questions or burning questions, just stick your hand up, intro me, and we'll just chat about whatever. And there will be an exam question on this. I'll write this afternoon, but I've got no idea what's going to be in it. So if you ask me questions on a topic, that could, when we discuss it, that could go in the exam. So yeah, this is your time. So right, that's a motorway by Munich. I put solar cells in. So firstly, about me. So basically, I'm not teaching ERP. I spend my life researching solar energy. And I specifically researched a type of solar cell called an organic solar cell or a plastic solar cell. They look a bit like this. They're sort of extremely flexible solar cells. And we'll talk about those later. And by the way, all these notes will go on Moodle. The video I'll put on the internet somehow, so you can relate write everything down. So this won't come from saying. Okay. And so you can look at what papers I published on this. So I do know the odd thing about solar energy. If you look at my Google Scholar stats. So what is this lecture? This lecture is basically enough to give you some background on solar energy. Now, solar energy is a really huge topic. I don't have time to cover everything. So this is like a tiny taste of what solar energy is about. And it's basically aimed at helping you decide whether or not to install solar cells as an engineer, when they might be appropriate to use, what type of solar cells there are. Just give you some background. Now, what this lecture is not is a device physics lecture. Okay. So, how many of you have taken Eric Larkins' course in electrical? Well, right, this is not that. Thank God. So, thank God. Okay, so what we're going to do is we're going to talk about, we've got to talk about something of it. We're going to do it like a very hand-waving manner with pictures and diagrams. So you'll get the ideas, but you're not, we're not going to mention the word burning or level. We'll be glad to know. So, again, I can't cover everything. There's 1.5 hours, 2 hours. Oh, by the way, we're going to have a break at some point because I can't talk for 2 hours, so we're going to have a break. If you want a deeper knowledge of solar cells and solar energy, I suggest you get this book by a lady called Jana Nelson, and that's actually a web link to Amazon with it's about 30 quid. And it's much more comprehensive than what I can cover now. So if you're going into the field, or if you're going to do a PhD in this area, this book's quite good. Okay. So why solar energy? So I thought I'd just give you my reasons. So I'm going to talk about some environmental science now for about 5 minutes. I'm not an environmental scientist, I'm an electrical engineer. So you can disregard what of this you want. But this is my view on why I work on solar, basically. So one reason that I work on solar energy is we're in effect, I'm going to put all what I'm saying now in quotes and sort of come back and correct it in a minute. We're basically running out of oil. So there's this idea of peak oil, where sort of here's 1900, we just sort of discovered oil in the ground and started pumping it out. And world production, this is world production, grows and grows and grows and grows. And because oil is a finite resource, at some point, this is going to be a Gauss state. It's going to be harder and harder to find it, and the world production will start crashing. If you think about places like China and India, their populations are growing. They need lots of oil. So we've got these sort of two contrasting problems. We've got increasing demand and reducing supply, which is going to mean huge increase in price and lack of availability. Now, it's sort of this graph's broken up into various countries. So here we've got Texas at the bottom. I didn't know that was a country, but anyway, basically production started about 1930, and then it's been gradually tailing off. And you can see basically all oil production sort of tailing off. And for example, we're shutting the North Sea gas fields now because they're oil fields because they're not economically viable anymore. Now, having said this, there's been sort of this boom in production recently, where oil's fallen to about $30 a barrel because we've got fracking. Okay, so that's like a blip on this curve. It sort of says, okay, so now oil production's going up, but oil's still a finite resource, right? It's still a finite amount of oil in the ground. So, okay, we're going to extend this by this curve curve for maybe 100 years. But over here, at some point, this curve will go to zero. And in the sort of lifetime of humanity, which is, hopefully a very, very long time, 100 years is nothing. So we've got to move on quickly. The other reason people don't talk about is this sort of Gaussian of coal production. Now, according to this paper here, coal production, or the amount of coal we got from the ground, is much lower. Please don't knock my camera. Thank you. It's my camera, by the way, so I get really upset if you knock it. It's not the university camera. According to this paper here, every time there's been a sort of new estimate of how much coal we've got from the ground, it's been revised down and revised down. So I think it's something like it's been revised down, something like 3 times by 30% every time there's been a new estimate of how much coal we've got from the ground. And this is because countries sort of either don't know or they like lying about how much coal we've got from the ground. So the point is, we're going to have this idea of peak coal here. So coal production will reduce, and certainly, it's just a matter of when. So if you could sit over there, thank you. Yeah. So it's a bit disruptive coming in late, so if you try to not do that. Yeah, and this is basic, so never mind the environmental argument. If we've got no energy, it's going to damage our economy. Okay? We're going to live, really hot and not having electricity. So this is a bad thing. The other reason that I think solar energy is very important is if you look at this curve here. This is called the Keeling curve, and it's measured by this man called Charles Keeling. And he spent his whole life measuring this curve, and he's now unfortunately died. But what he did is, in Hawaii, he measured the carbon dioxide concentration of, you can sit over there, please. He measured the carbon dioxide concentration of the atmosphere as a function of time, so every year. And what he saw is this sinusoidal variation of CO2 as a function of time. You might say, why do you have this sinusoidal variation? Well, this is due to effectively vegetation growth. So as if we get summer in the northern hemisphere or something, the plants grow, they're taking carbon dioxide, and then in winter they're taking less carbon dioxide. Can you see this gradual trend sort of marching upwards? We've got a gradual increase of CO2 in the atmosphere. Now this isn't scary, but the next slide is incredibly scary. So this is when he started measuring his data in 1960, and his career ended unfortunately somewhere here, but they kept on measuring the data. And you can see this periodic variation of CO2 in the seasons. But you also see effectively this exponential increase in CO2. So during this man's career, so just during this man's scientific career, CO2 in the atmosphere increased by 33%. That's crazy. 33%. And that's due to us. This is not due to anything else. This is due to mankind pumping out CO2 in the atmosphere. So this is a really bad problem. And so here's his data. So if we look sort of on a million or 1,000 year timescale, this is his data here. This is basically a rapid increase. It's basically a delta function, a rapid increase in CO2. And other clever people have been measuring CO2 not since 1960, but since 400,000 years ago. You think, well, how do they do that? What they do is they drill down into the ice like this. So here's the South Pole. Drill down into the ice and look at all the bubbles of CO2 that are trapped in the ice, and figure out what the CO2 concentration was, say, 1,000 years ago, and then measure this curve. So when you fit this curve with his data, so here's the old data and here's the new data, you see effectively since the start of the Industrial Revolution, we've got this massive spike in CO2. The CO2 has never been higher than it has ever been before. So this is totally scary. So then, if we look at global temperatures, I'm no expert on how we calculate global temperatures. We can see a corresponding massive rise in global temperatures corresponding with this rise in CO2. So this is totally scary. It gets even more scary when we look at CO2 output by country. So you might, if you listen to the news or the BBC or something like that, you might think that the United States and Europe pump out all the CO2 in the world and are responsible primarily for the death of polar bears like here. But we're not. So if you look at from 1960 to about 2010, this is CO2 output for the US. It's basically flat, right? Because they're developed. They've got their car, everybody's got a car, no more increase in CO2 from the US. If anything, it's going to go down because it's going to do things like have energy efficiency programs and stuff like that. Excuse me. Europe's pretty much the same. constant. But this is a scary thing. So let's look at China. Where's China? Any from China here? No? Yeah, you're from China, okay. So if we look at CO2 output from China, you can see it's basically an exponential that's gradually increasing. What this means is China gets richer and richer and richer. And everybody wants a car, you know, central heating, whatever. So CO2 output from China is rapidly increasing, and they're not even finished industrialising yet. They've got loads more time to go. So they're going to be pumping out loads more CO2. And if we look at India, so this is India, this little brown line. I don't know how many people are in. Any from India here? So I think there's 1 billion people in India or something. They haven't really caught on as much as China yet in terms of industrialisation. They're still, you know, they're very much behind China. So this brown section here is going to get at least as big as China, if not much bigger. So if we look at sort of the total of this graph, the majority of the CO2 being outputted now is from poorer countries. Okay. So this is slight. Lots of people shake their heads when I show this. So here's some poor people. Okay. And they're basically, they haven't even got enough money for running water, so they're going to a well and they're filling up their bottle of water. And what this tells us, if we think about this, is that expensive CO2 reduction strategies will never work. Okay, so have you had a lecture on carbon capture yet? Will you get one? Okay, well you can tell him this from me, it's rubbish. Because, right, the idea, here's a carbon capture power plant. The idea of carbon capture is you burn your coal and you stick the CO2 back in the ground and you bury it. Okay? But the problem with this is, if you think about it, how much energy are you going to need to stick that CO2 in the ground? Right? So you've got to burn more coal to stick the CO2 in the ground. I'm not an expert at this. I mean, I know from physics you're going to need more energy to stick CO2 in the ground than in the atmosphere, because you've got to sort of pressurize it and stuff like that. But I think you need about 40% more, which means the electricity these people are going to be buying from your power plant is going to be at least 40% more expensive than just sticking it in the atmosphere. And as these people are poor anyway, they're not going to do this. They're not interested in saving CO2 and sticking it in the ground. They can't be bothered. They're not interested in this curve. They're just interested about, you know, where the next drink of water is coming from. So the point is, whatever renewable, you go to over there, please. Whatever renewable technology you're trying to save the world with, it cannot be carbon capture. It's got to be cheaper than coal. It's got to be better than coal. It's got to be, you know, it's got to be cheaper for a better solution than fossil fuels. Otherwise, it's just not going to catch on, because the poorer nations are not going to be able to afford it. I'll put a big cross over this Toyota Prius one, because that's also a similar. That's not a world-saving solution, because it's more expensive than, I don't know, than a normal car. So that's not a solution. Okay. Any questions so far? Okay. So I think solar energy is a solution, because it's sort of the most direct way of gathering energy. We've got this massive sort of, effectively, fusion reactor in the sky. And all we need to do is harvest this energy by sticking a few solar cells on our roof, and we've got our energy. So I'll show you, this graph I think is very important when you're thinking about solar energy. Excuse me, I just have a cough. So this sliver here, so I made this graph some data I found. So this sliver here represents total world oil production per year. So that's all the oil that Saudi Arabia, Russia, North Sea oil produce per year we burn in our cars. This sliver here represents what's left in the ground. Okay? So if you divide this slice by this slice, I don't know, 100 times maybe, 200 times maybe, that's 100, 200 years left, worth of oil left. This yellow section here represents the amount of energy in sunlight as instant on the Earth's surface every single day. Okay? So all we've got to do is capture a tiny, tiny sliver of this energy, and we've got all our energy needs sorted. There's a huge amount of energy in the sun. Now, I genuinely think that all these other renewable energy technologies are just going to fall by the wayside as soon as we get really cost-efficient solar panels, because there's so much energy in sunlight and they're so easy to install. I really do think this is the long-term solution. So going out for 100 years or so, I think everything will be powered by solar. At least that's my view. And so looking at typical solar energy fluxes, so this is sort of maximum power flux in the Sahara. So if you're in the Sahara, you sort of lay like that, and you have a 1 metre area square of your body, you get about 1,500 watts per square metre. So that's 1.5 electric fires per metre. That's a huge amount of energy. Okay. In the UK, and so if you average that over night time in the Sahara, it's about 400 watts, which is still a lot of energy. Okay. You don't need 400. I don't need 400 watts an hour. You know, I might need 100 to run that projector, but I don't need 400 watts. And the UK, the average, so averaged over like day and night and cloud and rain and all that is about 100 watts per square metre. And you think about that in terms of sort of a typical house roof. So a house roof is usually quite big. If your solar cells are only 15% efficient, generally that's about enough energy to run a family. Okay, so if we had solar cells on all our roofs, problem solved. It's really that simple. So here's some, so feel free to interject and question it. I'm very happy to answer questions, especially if you disagree with anything I'm saying. So where might you find solar cells? So this is a town in the south of Germany called Freiburg, and they're very into their green energy. And they're built to areas of the city with just solar cells on all roofs. So this is, you see solar cells on all the roofs. And as you go through the British countryside on the train, you start to see, or I've started to see more recently, sort of big solar power stations. So these are literally arrays of solar cells on land. So I think it's a bit of a waste to put these solar cells on land, on beautiful farmland, but there's no reason why you couldn't put them on top of a car park or something like that. So, you know, these are sort of industrial scale solar installations that you find in the UK. And also, you can put them on cars, but I think it's a bit of a silly idea, because then you've got to move your solar panels as well. So it's much better just to have them, or in my view, to have them stationary and just connect into the grid so everybody can use them. Right, sunlight. So I thought, any questions about last bit? Okay, right. So I thought we'd talk about sunlight. So this is a very interesting map. This is a map. Also, what somebody did is they took they got the cloud cover of the world from satellite images over the last, I think it was like 10 years or something, and calculated the sun's radiation on all parts of the Earth, and then calculated how much sunlight we actually get through to the Earth. And this is a map they drew. And if you look at the very, very red areas, like the Sahara, somewhere there, it's about 300 watts per metre squared on average, including nighttime. Whereas if you look at the UK, so here's the UK in blue, we still get, you know, we're in 150 watts per square metre, so these are still useful energy numbers. And the most interesting thing about this graph is if you see these dots here, 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 if you took those areas and covered them with solar cells, the total is about 18 terawatts. And this is enough energy to run the whole world. So we need to burn no more coal, no more gas. We could run them on solar. So this is how powerful, or how much energy there is in sunlight, even in the UK. So what does the solar spectrum look like? Well, if you go to space in a satellite or in a space shuttle, the solar spectrum looks like, it's called a black body radiation. Who's a physicist here? No? Anyway, a black body curve looks like this. So here's wavelength up here, and it basically looks like a cow that's been pushed on in time, so it goes like that. And the yellow curve is basically the sunlight you receive on your satellite from the sun's radiation. And what's very interesting about this is when you then go, and that's called, by the way, the AM0 spectrum, that's the official name for it. And when you go down to Earth, to where we are now, the spectrum starts to look like this. So it's a red section. And you can see the sort of notches taken out of it here, here, and here, and here. Now this is mainly due to water vapour in the atmosphere. So here we've got some oxygen taken out this section here, H2O taken out this, H2O taken out this, water, a bit of CO2 taken out here, a bit more H2O here. So you see the spectrum we have on Earth sort of basically altered than what you'd expect in space. And this is called the AM1.5 spectrum. So there's a special definition of what standard sunlight is. And I can't remember exactly, but it's sort of something like a particular place on Earth and measured in a particular direction at a particular time. And whenever you test a solar cell or something like that, you always have an instrument that produces the AM1.5 spectrum, and that's sunlight in the sun. And you can download this spectrum on the internet, plot it, and use it for your calculations. So if we look at this, so this is wavelength. So it's always very hard to think about what wavelength means. So here's what we can see. This is what you and I can see. So here's like UV. So I don't know, you've got some dark purple in your shirt there. So that's about that colour. And then there's red at this end. And we can sort of see blue. You know, this is all what we can see. There's quite a lot of energy in this section of the solar spectrum. But I'd say more energy out of the visible spectrum in the infrared. So between, say, 750 and 2,000 nanometers, there's a lot of energy. And also in the UV, so these are the highly dangerous photons, high energy photons that burn in the sun. There's quite a lot of energy there too. but they're usually filtered out by even by window glass. Okay. So I found this graph, and I thought this was quite a nice one to show you actually. So this shows you, this is a plot of the solar spectrum as measured on Earth, but for different atmospheric conditions. So you see the basic shapes from that. So it's sort of that. And here we've got, so the blue is radiation on a day with blue sky. And what else do we have? Late afternoon sun is this. And we've got cloudy day somewhere. Light cloud is allegedly this, which on this graph apparently is higher than the blue sky. I'm not quite sure why. Maybe it's because clouds scatter radiation, so it sort of makes a uniform light. I don't know. But I just thought it was an interesting graph to show you how basically weather affects your solar cycle. So this is a quick question. What's this?
Mars.
Yeah, well, it's not. The correct answer is the sun from Mars. So you notice it's a lot smaller. Okay. So you know, if this was Earth, the sun would be like that. But it's a little dot on the horizon because it's a bit further away. And you can calculate effectively the solar radiation on Earth if you know. If you know, so I'm going to get some maths into this. If you know the power that the sun kicks out, so the sun kicks out this, and then assume it's sort of a 1 over d squared relationship. But light, you know, as light spreads out, the intensity increases 1 over d squared, and you calculate the intensity at the Earth. And you also need to notice when you're installing solar cells that obviously the Earth's axis is tilt, sort of 23 degrees, so you get different amounts of sunlight in winter and in summer. You think, oh well, it doesn't matter. But if you're in Finland, North Finland, it's dark all the day in winter, and it's light all the day in summer. So it doesn't mean they don't use solar energy in Finland, but it just means it works in the summer really, really well, and you need something else in the winter. So if we do that calculation, pop these numbers in, we can get about 1.3 kilowatts per metre squared out, which is what we get in Sahara. Yeah, so could ask you in the exam, for example, to calculate on Mars. I'll give you the distances, pop that in. Right, now I'm going to talk about some physics, basically. We're going to talk about solar materials, and we'll talk about sort of harvesting light using semiconductors. So, if we look at a metal, so this is just a piece of metal, any piece of metal. If we look at that, the surface of that metal, you can think of it, I guess you've all done this in physics at school. These sort of metals are basically a sea of electrons. So there's positive ions, but effectively you can think of metals as a sea of electrons. Is that a familiar picture for everybody? Yeah? Right. So we can draw this in sort of an energy level diagram. So energy is going up here, and this is the surface of the metal at basically a very, very cold temperature. And we have all these electrons, so these red ones are electrons. They're just sort of at the surface of this metal. And if we want to rip an electron off that metal, so if we want to rip from, I don't know, here's a metal. If we want to take an electron off this piece of metal to a distance of infinity, we need to put some energy in. And typically, the energy you need to put in to do this is about 3 volts. So once you start applying 3 volts to metal, round about that, you rip charge carriers off the surface. And you take them to a distance of sort of basically infinity. And this is called the electron affinity. Okay, so this is the energy you need to take 1 electron from the surface right away from metal, so it no longer feels the interaction with metal. Now, solar cells are not made from metal, they're made from a different material called a semiconductor. And this is a very special type of material, because not only, so this is a semiconductor, I think this is gallium arsenide or something, or it might even be silicon. So here again are electrons, just like in the metal, and here's sort of an edge. But semiconductors have a very, very special feature in that they have a forbidden region. Okay? So they've got something called a band gap. So in this band gap, or this forbidden region, you are not allowed to have electrons. Now, it's forbidden, absolutely forbidden. And basically it's sort of forbidden through quantum mechanics. It's just not, they cannot exist there, it's not possible. But they can exist away from the band gap, so above the band gap. So, this is how a semiconductor absorbs photons. A photon comes in like this. Okay, so this is, I don't know, blue light or something like that. And an electron, so here's an electron, absorbs that energy from the photon, and it gets promoted up through the band gap to something called the conduction band. So
this electron is not allowed to exist here, but it can exist here. But it's okay because this photon just kicks the electron bloop, from here to here. And you see we've now got a gap here in this sort of sea of electrons. Because we've taken away a positive charge, we've sort of got an imaginary, because we've taken away a negative charge, we've got sort of a gap where there was an electron. And this is called a hole. And it's sort of got a positive charge. So we've now got a positively charged particle here and a negatively charged particle here. And this is called the valence band in a semiconductor, and this is called the conduction band in a semiconductor. And what you really need to think about, or remember effectively, is that in a semiconductor you have both electrons and these positive charges in the same material, and you can promote charge from the valence band to the conduction band by the absorption of a photon. Are there any questions on this? So I'm not. Some of you have covered it. How many of you is it really familiar? Hands up. Okay, how many is it sort of new? Okay, so you're right with it? Yeah, okay, it doesn't get much harder. Right, so band gap, valence band, conduction band. Absorption happens through motion of electron from the valence conduction. So the band gap of silicon is 1.6 eV, I think. I think it might be 1.65. It's about 1.6 eV. And eV is a measure of energy. Okay. It's called an electron volt. So when a 1.6 eV photon comes in, which I think is red, or deep red, it can very happily promote an electron from the valence band to the conduction band. However, when a 1.0 volt photon comes in, so a low energy photon, it doesn't have enough energy to kick this electron all the way up to the conduction band. It just doesn't have enough. And because it's not allowed to promote this electron like halfway, because this is a forbidden region, nothing happens. This photon just passes straight through the material and no absorption happens. So what this means is semiconductors don't absorb energy below the band gap. So all energy, so if this is 1.6 eV, all photons below 1.6 eV will not get absorbed, and all photons above 1.6 eV will get absorbed. Okay. So if we look at the absorption spectrum of silicon, you can see it's very, very thin. So this is absorption on a log scale. So basically between 0 and about 1.2 eV, no absorption at all. But remember this is a log scale. And then we go to 1.6 eV, absorption is still pretty terrible because this is all below the band gap. And then once we start getting above that 1.6 eV, silicon starts absorbing very, very well because we can promote these electrons from the valence band to the conduction band. So that's why absorption, or silicon has this particular absorption spectrum because of this band gap and this forbidden region. Everybody happy? Yes, questions? What?
So would the solar panel be more efficient if the material used had a less EV, what's it called?
Yes.
Threshold?
Exactly. It's a little bit more complicated. You're absolutely right. That's why I'm showing you this. And we're going to make it a little bit more complicated, and we're going to sort of talk about the arguments for and against that in a minute. So that's a very, very good question. Are there any others? So do ask questions. That's pretty good question. Yeah, go for it.
Is the hole actually a real particle, or just
Is it a real particle? Quite a philosophical question, isn't it? People certainly do. What's this? Yes. Is my answer. I think people spend lots of time smashing positive and negative charges together in particle accelerators. So I guess it is real. But I'm not enough of a physicist to give you a definitive answer. I'm an electrical engineer. I don't know. I treat it as one in all my simulations, and that works. But yeah, ask a physicist. Okay. Right. So, as the man said, what this means is, so this is actually not an EV, this is in nanometers. We'll do the conversion between nanometers and EV in a minute. What this means is silicon can absorb excellently all energy, like in this part of the solar spectrum, but all of this lot, about half of it, just passes through silicon. It doesn't even see it because it's below the band gap. So there's one other case which sort of starts to answer your question. So if we've got a band gap of 1.6 eV and we've got a photon of 3 eV, will it get absorbed? Yeah, right. There's an issue. Watch this. This photon's got loads of energy. So what happens? This electron gets kicked way up into the conduction band, right, and it's got loads of excess energy. Because we've not just promoted it to the conduction band, we've promoted it to the conduction band plus some, okay? And so we've absorbed it, that's fine. But what then happens is this electron relaxes, it sort of just loses energy, and it literally loses this energy through giving out heat. So it literally loses heat, so your semiconductor gets hotter. And then it settles down at the conduction band edge, which means we lose all of this energy. So this energy has just lost the heat, and it's called E-loss. Okay? So it's just like gone. It's not, we can't do useful work with it. So what this means is that the optimum wavelength to absorb light is at 1.6, and everything above that, we're always going to have a certain amount of energy lost from the photon. Okay? Yeah? So, how many are good at converting between EV and or energy and wavelength? I thought we might have to practice, I think. So the way you do it is you use Planck's constant. So Planck said basically energy is equal to hf. H is the frequency of light. And we know frequency, or C equals F lambda. So if we pop this into this, we can go energy equals H times C over lambda. And H is Planck's constant, so 6.6, 2 times 10 to the minus 34, and 3.8 is about the speed of light. So using this, we can calculate between energy and lambda, or wavelength. So I would like you to calculate what wavelength 1.6 eV is in, so I'd like to convert 1.6 eV using this equation to wavelength. And you're going to need something else. So EV So EV is a measure of energy, so it's electron volt, and it's 1.6 times 10 to the minus 19 joules. So in this energy term, you're going to have to put in 1.6 times 1.6 times 10 to the minus 19 to calculate how much energy it is in joules, because this expression links in SI units. So to change EV to SI units, you just need to multiply by 1.6 times 10 to the 19. Shall I say it again? Or shall I write it? I'll write it. So 1.6 EV equals 1.6 times 10 to the minus 19, that's the energy on electron, times 1.6. I'll put 1.6 EV equals joules. So converting it to joules, using 1.6 times 10 to the minus 19 times 1.6. Okay, and then after you've done that multiplication, stick that in E and calculate what happens. Go. If you're first years, I'll give you sweets. But I thought to speed you up. But as I thought you're fourth years, I won't bribe you. I'm not going to give you that long. So we've got a man posting up there. Good stuff. Anything here? Did you get it? Yeah. You need to see. Meet the second. I wrote this last night. So. Yeah, people like something means spread. Sorry. What are we doing here? Anybody got an answer for me yet?
7.76.
Okay, let's write this out. We'll see if you're right. I'll get 3 answers. Compare them. What do you reckon? What do you reckon yours is? What is it? What do you? Rory?
7.76.
76 times
10 to the minus 7.
Anybody else?
Yeah, same.
So, you sit next to him. That's cheating. Anybody else? Anybody agree? Yeah? Okay. So this is 7.76 times 10 to the minus 7 meters, which a nanometer is 10 to the 9 meters. So that's about 700 nanometers, which is sort of far infrared, which is actually about what we got here with the absorption spectrum. Okay, so that would be a very easy example, actually, which wouldn't take me long to write this afternoon, so that'd be a good one. I don't know. And there's the working 7.73. Yeah. So now, how many of you know about diodes? Yeah. How many of you don't know about diodes? Yeah. Okay. So what I'm going to do is I'm going to step you through diodes, but not in the sort of semiconductor physics way, like in really, really basic, this is what you need to know way. And then we're going to go from diodes to solar cells. And what we'll do is we'll stop in about 15 minutes. We'll have a coffee, and then we'll crack up, or I'll have a coffee at least, and then we'll crack up. Okay? So, fundamentals of diodes. So I need to teach you about diodes before we talk about solar cells. So, diodes are really, really fundamental parts of electronic device, and they're everywhere. Like the modern world would not function without diodes. And effectively, a diode can be used for power rectification. Work it's a bit tricky. They're using light-emitting diodes, so LED is light-emitting diodes. So that's an LED. LEDs everywhere. It's probably on your watch or on the camera or whatever. Lasers. So this is a laser. And so you get laser diodes. They're diodes too. And solar cells are also diodes. So if we understand diodes, we can understand all these classes of electronic device. Now the ones we're going to start off with are these power diodes, because they're easiest to understand. So they don't give out light or absorb light. They'll tell us about diodes. So before we can understand power diodes, let's think about AC and DC current. Now AC that you get out of the wall socket here is an alternating current, which means it goes, it's a sinusoid, so it goes on, off, on, off, on, off, on, off, about 100 times a second. And if you imagine trying to listen to your music on an MP3 player, and I know it says 5 volts there, I'm assuming it's stepped down. If you try to listen to music on an MP3 player that was switching on and off 100 times a second, it'd be pretty irritating, because you get to like hundredths of a second to retract and turn off, and then turn back on again. So most of our modern devices don't run on AC, they run on DC current, so everything runs on DC. So somehow we need to go from the sinusoidal waveform to basically a DC waveform, this sort of direct current, so our device stays on and doesn't turn on and off 100 times a second. And to do this, we use a diode. And this is the picture of a diode, this is a symbol, and here are some diodes. And if you look at a diode, you know which way around it is, because it's got a line. So here's a line, here's a line, here's a line. And that line can be lined up with this bit here, so you always know which way around it is. Except this one, I've got no idea. So you can think of a diode in its sort of simplest way as a one-way trapdoor for charge. Okay? So if you push positive charges through this way, they go through the trapdoor that is the diode and come out the other side. But if you try and push charge through the other way, this way, the trapdoor shuts effectively, so it's like a trapdoor in your head. It's not a real trapdoor. And the charge can't get through the diode. So it blocks charge in one direction and it lets charge through in another direction. So you can think of a diode a bit like a one-way cat flap. So if you've got a cat at home with one of those little twiddly knobs on the bottom of the cat flap, so you can let the dog or cat in, but not out, or let it out, but not in. You think of it like a one-way cat flap with a charge. So let charge through one way, but not the other. Okay? So here's a circuit with a diode in it. So here's a battery. If we connect the battery up this way around, charge will flow through the light bulb, through the diode, and back around, blah, 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 and we get light. If we change the direction of the battery, so charge tries to flow this way, it won't get let through the diode, the light bulb won't light, and we won't get any light out. So with a positive voltage it turns on, with a negative voltage it turns off. Good so far? Yeah. So the current voltage curve for a diode looks like this. It's off, or it's on. Okay? So in one direction, no current. In the other direction, so when we put positive voltage on it, basically let through any amount of current we want, so infinite current in the ideal diode. Okay? So when we try and do rectification, so this is called rectification with our diode. So we get our mains here. Here's our nice sinusoid of our mains, and we stick a diode in the way, and we put here we measure the voltage. What we'll get is we'll get a series of humps or hills that will go on. It won't let through this negative voltage, so it'll be 0. It'll be on, 0, on, 0, on. So it's only letting on letting through this part, not this part, this part, not this part, this part, not this part, this part, not this part. And that looks a little bit like DC. I mean, it's not negative, right? It's close to DC, but it's not really DC. So what we do next, who's electrical engineer, what we do next to make nice DC? Capacitor, right? So we add a capacitor, boom. So we add a smoothing capacitor here, and this sort of stores, basically, the capacitor basically sort of stores charge from this pulse, keeps the voltage high whilst the power's on, and then recharges. And so it's sort of DC. You don't need to understand. I'm not trying to teach you making power supplies, but basically, stick a capacitor in. You get more or less DC, and our device stays on. Okay, all good. So that's one use of the diode. Now we're going to go from diodes to solar cells quite quickly, in 5 minutes. So the ideal voltage characteristics of diodes look like this: so off and then infinitely on. Now this isn't really a realistic voltage, current voltage curve of any device, because no device has sort of infinite connect through infinite current. So here we connect through, the curve goes straight up. And if you think about objects like me, or the table, or a diode, or anything, we've all got resistance. Okay? We've all got a small amount of resistance associated with us. So I've got a big resistance because I'm made of water. A piece of metal will have a low resistance. But diodes are no different. They're made from a semiconductor. Semiconductors have some electrical resistance associated with them. So we think of a diode as an ideal diode. So this is this curve that goes off and on, in series with a resistor. Okay? And this resistor is like, I don't know, a few ohms. So what this does to the JV curve is it moves it from being ideal to non-ideal. So if you measure the slope of this curve, you get the resistance of the diode. And what all this means is that we can only let through a certain amount of current for a given voltage. Excuse me. Any questions so far? Everything clear? Everything clear back? Yeah, good. Right, so this is as far as semiconductor physics goes for this lecture. Diodes are made of two materials which are semiconductors. They're special types of semiconductors. And they're made of an N-type and a P-type semiconductor. The N-type is called an N-type semiconductor because it has got a negative charge in it. And a P-type semiconductor has got a positive charge in it. Okay? And when you put those together, like this, so the diode looks a bit like this. We've got a region of positive charge and a region of negative charge. So this is really diodes in cartoon. So I'm sort of cutting out all the physics. When we put those together, because there's lots of charge in them, because there's lots of charge in this diode, the diode intrinsically has or produces a voltage just because there's this charge in it. So it's got charge in it, and therefore, because of this charge, you always, when you measure the voltage between there and there, you always measure a voltage between about 0.3 and 0.6 volts. It's like a rule of physics. In fact, it's Gauss's law. And Gauss says when there's charge in an object, it will have a voltage in effect. I'm not going to go into this in detail. But the point is, there's charge in here, and you get a voltage. Clear? Okay. So, because there's a voltage produced over our diode, a very, very small voltage, like 0.6 volts, we can extend our diode model. So we've now got the ideal diode, the resistor, and a battery, a little battery, 0.6 volt battery. So we can now go back to our JV curve, or our current voltage curve, and change it to include this little battery. Okay? So this little battery offsets sort of the zero voltage point by whatever the voltage of the battery is. So it's like 0.6 volts in this case. Which means what will happen is we apply the voltage to the diode, so 0, 0, 0, 0, gets positive, it's still off, it's still off, gets to 0.6 volts. We overcome that little built-in voltage, and then it switches on, and then we're into this like resistive regime where we're basically the current's increasing proportionally to the resistance of the diode. So we've got three circuit elements. I'll just repeat it again. Ideal diode, responsible for turning on. Little resistor, responsible for the slope. Little battery, responsible for basically effectively pushing this curve off to positive voltages. So that's like a relatively good diode. So what comes next? Who wants a break now? Who wants a break in 10 minutes? 10 minutes, yeah? Okay, right, I'll do another section. So now we understand diodes. And diodes are basically the fundamental element of the solar cell. We can now start to understand solar cells. So actually 10 minutes is a good place to start. So let's go from diodes to solar cells. So here's our diode again. Okay. So this time I've just drawn it as a box with a positive and a negative terminal. Okay. So we remember we've always got this voltage of 0.6 volts over our diode because of the charge inside it. Then imagine we've got the sun. Okay. And the sun shines photons on our diode. Right? And the photons get absorbed, and we generate an electron and a hole, just like we did in the cartoons previously. And because we've got this sort of voltage over our diode, the positive charge that gets generated gets drawn to one terminal, and the negative charge that gets generated gets drawn to the other terminal. So because we've absorbed this photon, we've now sort of forced a hole this way and an electron this way, using this electric field. Then if we shine lots of photons into our diode, they all get absorbed, we generate lots of positive charges, lots of negative charges. This field forces the negative charges to go this way and the positive charges to go this way, and we get current flowing in our external circuit. So it's all driven by this sort of built-in potential, effectively, in our diode. So this is, in effect, a solar cell. That's all there. It's just a diode. So, we can calculate how much power our solar cell, or diode, is going to produce. Because we know power equals I times V, number of photons is n, A is the area of our diode or solar cell. So we go power equals A, area, times the number of photons per square metre, times the charge on an electron, times the voltage, which is the potential drop, or the built-in voltage of our diode, and we can calculate how much power we'll get kicked out by the diode. So this is a question for you. A 0.1 metre squared solar cell, so it's actually a diode, it's kind of a diode, produces a voltage of 0.6 volts and absorbs a spiral, 1 to 20 meters, photons per metre squared per second. If the charge on electron is 1.6 times 10 to the minus 19 coulombs, how much power will it produce? So how much power will our diode produce? And how many Hello Kitty toasters will it power? I'd like you to work that out. So I'd like to know how many Hello Kitty toasters our diode will power. Go! And incidentally, so this is just if you shine light on any diode, so whether it's if you actually shine light, if you take apart this laser pointer and you extract the diode and you shine light on it, it'll actually act as a solar cell. It'll actually absorb photons. So all diodes can act as solar cells. So you're just going to multiply the numbers together and give me an answer. I don't think I even know what it is, so it can't be that wrong. You got an answer?
It's probably 0.096.
What watts?
Yeah.
0.096. So how many Hello Kitty toasters is that?
0.
0. Okay. So the answer is 0. So we can't. It's basically a rubbish solar cell because we've got it doesn't produce much power. So yeah. So is that what you got? About yeah. So 0.06 watts. So it's not enough power to run anything, like literally anything, let alone a toaster. So what could we do to make our diode or solar cell produce more electricity?
Make it bigger.
Make it bigger. So this A, right, increase the area. Yeah. So here's our diode with a times area like that big, and here's our solar cell with a massive area like this big. So that's all. I don't know if we've got a better picture. So that's all this thing is. This thing is just literally a diode, but just like squished and spread out a lot. So that's all it is, and it's got this sort of region of positive charge and negative charge. So solar cells are diodes, and they look a bit fancy because they've got this metal strip on the top. But all that is nothing clever. It's just to help get charge very quickly and efficiently. It's been generated out of the solar cell. Yeah, so it's sort of improved conduction. Okay. So now you know what a solar cell is really. Sort of fundamental physics. So I'll just do it at the end of this section. I'll go and get a coffee. And obviously, another way to increase the power that's kicked out of this solar cell is by increasing the voltage. Now, this voltage of 0.6 volts is sort of fundamentally the material that you've got. So silicon, it's always about 0.6. The other semiconductors is lower or higher. And actually, quite interestingly, if you buy different coloured LEDs, so green, or red, orange, they have different turn-on voltages. That's all because of sort of how this charge distribution inside them. So anyway, what we can do is get more voltage out of silicon solar cells. Is literally slap them in series. So we have 0.6 plus 0.6 plus 0.6 plus 0.6, just like batteries in a device. And you can build up to quite big voltages like this and quite big currents. So this is an example. So this is called a solar cell. This is a diode. Okay, so this is just a single diode. What you can do is you can put these in solar modules. So each one of these is a solar cell. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 1, 2, 3, 4, 5, 6. So 60 solar cells in this solar module. And you can sort of arrange them together in series. So if you attach one of these strings in series with another one, you can sort of increase the current and the voltage. And out of these rates, you can get actually hundreds of volts and hundreds of amps. So you can get really a lot of kick out of it. So if you're building one of these systems at home, don't do it in the daylight, because it might hurt a lot. I think this is the last slide in this section. So the one thing to know, or to know about these solar cells, is that basically when somebody says, my solar cell is 20% efficient, it probably is. This thing is 20% efficient. But when you build it into a module, you get some loss, because you've got to connect these things together with wires, and these wires have a resistance. And also, to build these modules, you've got to put a piece of glass over it to keep off all the bird rubbish and trees and stuff like that. So you get some reflective losses of light on the surface of the solar module. So the efficiency of the module is always lower than the quotient efficiency of the cell. And then what you do is you connect these modules together in sort of banks like this, and you have more wires connected together with more resistive losses. And then you connect these sort of strings of panels together, and then you connect it to a grid, which is the mains grid of your house, with some type of converter that goes from DC, so these kick out DC, to AC, and there'll be losses there. So the point is, at every stage in this process, there'll be losses. So a 20% efficient solar cell might mean a 10% efficient system. And when people talk about the efficiency of solar systems, they say, oh, it's 10% or it's 20%. You might think, oh, it's rubbish. Why? I'll talk about that later. But it's not actually rubbish, because it's 10%, like it's a free 10%. Like you've not had to dig it out of the ground, so it's a free 10% of energy. So it doesn't matter really how efficient it is. It's free. It's sunlight. So what we'll do is we'll have a break, and I will run to Coast Cafe and get a coffee, and then we'll start again. So the break time is determined by the queue and my ability to run. Okay? Right, so go. So this is the diode curve in the dark, and basically this is without any photons hitting it. So it's zero current, zero current, zero current. And you turn it on, and it switches on. However, when we apply some sunlight, when we switch the sun on, because you do, what happens is the sun starts generating current. The sun starts generating current, and what happens is at zero. So for a normal device, obviously at 0 volts in the dark, it can produce no current at 0 volts, because otherwise it would be producing energy. But when we apply the sun, we start producing current at 0 volts, so we get some current out. And we also notice the whole curve basically shifts down because we're producing current, so it's all just offset and pushed out. And when we turn the sun up brighter, so it gets to midday, the curve shifts down even more because we're producing current. And this point where it crosses the x-axis is pushed back, and even more. So this is a general trend with any solar cell current voltage curve. Increase the sun, and you get more current. You got a question? Yeah.
So what happens after it crosses the 0 line?
Where?
The current?
Here?
Yeah, so basically it goes up and then crosses the x-axis?
Here. Tell me the question.
No, the x-axis.
There? There?
Yeah, so basically when they
There.
cross the x-axis, what happens?
So if you imagine you've got your diode with the sun shining on it, what this curve is basically doing is applying a voltage, so it's applying like 0.1, 0.2, 0.3 volts. And we're just looking at how the solar cell basically reacts. So this is actually a special point. And we'll talk about this in a minute. And I'll get you to think about where the solar cell produces the most power, which I think might even be on the next slide. I think you're always one slide ahead. So, yes, you are exactly one slide ahead. So this point here is called VOC, or voltage of open circuit. Okay. So if you've got your solar cell and you just leave it on the ground, connect no wires to it, no current flows in the external circuit. It's called VOC, so open circuit. It's not connected to any external load. The converse situation is where you get the cables of the solar cell or the solar module, and you stick them together, so you make a short circuit. And this is called a JSC, or current of short circuit. So here we've basically got maximum current, and here we've got maximum voltage. So you'll know power. We'll see this on the next slide. So you'll know power equals current times voltage, right? How much power will be produced here? How much power will the solar cell produce here? Zero, right? Because voltage is, say, 0.6, current is zero power. How much power will be produced here? Zero. So current is maximum, voltage is zero power. The place where we produce maximum power is here. And it changes as the solar cell temperature changes, and it changes the sun intensity changes. But basically, at this kink here is where we have sort of maximum current and maximum voltage. So this is where you want to be sort of operating the solar cell at most of the time. And generally speaking, you attach your solar cell to some kind of power electronics that sort of keeps the solar cell running at its maximum function efficiency. Okay. So now let's look at different types of solar cells. So what this is basically a very, very quick tour and a very sceptical view of modern solar cell research and modern types of solar cells. So I'm going to tell you all the bad things about all the different types of solar cells and let you sort of present the problems sort of clearly to you, and so you sort of have an idea of the state of the art and where people are working and what we're thinking. So as you go through the countryside, so the British countryside or the German countryside, you might see solar cells on the roofs of houses. And I think it's actually US. But this is sort of a typical thing you might see. So blue silicon solar cell. And this blue colour is always indicative of silicon. And that's what you normally see on roofs. And they're between 15 and 20% efficient, which is actually quite good for a solar cell. We'll talk about why a bit later. And they have a lifetime of typically between 10 to 20 years. So you're thinking now, they're on roofs, they're good, you can buy them in the shops, you can even buy them on IKEA, 20-15% efficient, you get free energy, last 20 years, what's not to like? Brilliant, solved our problem, let's just make more of them. Okay, that's one answer. I'll tell you why they're slightly problematic in a minute. So if you thought that, you'd be right. So there's this sort of rule or law called Swanson's law, I think that's how you pronounce it. And what he noticed that as the number of solar cells that we produce in the world goes up and up and up, so the production costs go down, down, down. And this isn't just true for solar cells, it's true for mobile phones, for example. So, you know, if you ask somebody in 1970 to make you a supercomputer that fits in your pocket, and you can talk to somebody that, on the other side of the world with this device, it would be $1 billion research project, and that one mobile phone would cost, you know, a fortune. But as sort of mass production and sort of mass production and sort of like everybody wants one has optimised effectively all the inefficiencies out of the mobile phone manufacturing process. We've got cheaper and cheaper and better, and now we've all got supercomputers in our pockets. So the same thing happens with anything, for aeroplanes, pencils, solar cells. So as you produce more of them, the price goes down. So the cost of, I think this is $1 per watt. So this is, when you talk about solar cells, you don't talk about the cost of the solar cell. You generally talk about the $1 per watt. So how many dollars does it cost to produce 1 watt of electricity? So in 1976, when we first started to make them, you know, there's maybe one around, and then it cost maybe $100 a watt. And as we continue to manufacture more and more of these solar cells, the price has started to sink, and we're now around about $1 a watt, about. And that's about the cost of coal. So in some places in the world, solar energy is cheaper than coal and nuclear. So it's on that downward trend. So you can see in a few years, solar is going to be almost certainly a ubiquitous source of energy. And I think so every decade, in production, so you are at something like price drops of 20%. So we're almost down the downward cycle. The big problem with silicon solar cells, though, is the energy you need to put in to make them. So to make silicon solar cells, they're made of something called silica, which is effectively sand. It's not, but it's basically what it is. And what you do is you get this silicon, you purify it into these ingots of silicon. And this thing here is not a bit pure. It's like 99.9999, so it's 9 nines pure. It's that pure, it's extremely pure. And to make an extremely pure material, you need lots and lots of highly energetic steps. So there's double hydrogen through it, heat it up. It's a multi-stage process, and it consumes a huge amount of energy. So to go from basically silicon to your solar cell, you need some incredibly large amount of energy. And I've put 2 gigajoules per square metre. I'm not sure if that's right, because I can't find the reference I found for this. But it's a huge amount of energy you need to go from sand to a solar cell. So this is a big problem. And where do we get this energy from? Well, this is a picture of Trent Power Station through the mist. We get this energy from effectively burning coal. And a very interesting study a couple of years ago said that if you added up all the energy that we've used by burning coal effectively to make solar cells since 1970 to about 2010, solar cells have only started to make back that energy in the last 2 or 3 years. So they're an incredibly intensive thing, energy intensive thing to make. So when you see these solar cells on roofs, you think, well, that's very nice. Where does that energy come from to make that silicon? It's a hugely energy expensive process. So this is sort of driving a search for lower cost materials. So there's lots of research groups working on lower energy materials. So they're not materials that basically cost about as much as a crystal to make and will harness the sun energy. So that's sort of the aim. And this is a graph. This is a very famous graph put out by some people at NREL, which is the US National Renewable Energy Laboratory, I think it's called. And we'll expand this. Boom. And what this is quite an interesting graph. Along the bottom we've got time. So we've got 1975, and here we've got 2016. I got this up. And they upload this to Wikipedia every few months. So they publish it in a journal and upload it to Wikipedia. So you can always see the latest graph. So it might be a little difficult to see, but we've got on here different colours to represent different solar cell technologies. And on the side we've got efficiency. So let's look at silicon. So silicon crystalline. Okay, so this is I can't read very well, but this is I think silicon. So they're derivatives. So the efficiency of solar cells has basically started around 12% in 1985 and gone up to around 21% today, which is the type of thing. And there's some very efficient solar cells around. So there's sort of multi-junction cells up here that started life about 2000. The efficiency has gradually increased to about 46%. Now, it doesn't really matter how efficient the solar cell is, because it's always that ratio of cost produced against the energy it produces. So, for example, if your solar cell is massively inefficient, but it's basically free to make, or incredibly cheap, it doesn't matter that it's really inefficient, because the energy it harvests is free. Okay? But if your solar cell is super efficient, but it costs £1 million per square metre to make, then that's a problem, because it's going to take ages for that energy for you to make that $1 million back. So there's always this sort of trade-off with solar cells, like efficiency versus how much it costs to make. So you should try to optimise that dollar for watt of electricity, not necessarily the cost. So although these are efficient, these solar cells at 46%, they're very expensive, so it's not necessarily something you want to put on the roof. So now we're going to look at different types of solar cell. So one alternative to the silicon solar cells is something called the plastic solar cell, or the organic solar cell. And that's actually what I spend my life worrying about. And organic solar cells are effectively made of plastic. They're actually made of plastic materials, like this plastic here. So how they're made is effectively just a layer of transparent plastic, like this. And you evaporate onto it some type of conductive oxide, so like Indian tin oxide or something like that. And then you deposit on this Indian tin oxide a layer of literally plastic molecules. And they're a special type of plastic called, well, they're conducting polymers. And they look like this, so this is effectively a polymer that conducts electricity. And this is a small organic molecule that also conducts electricity. And these materials effectively harvest the sun's light, and then you pop on a metallic back contact, and you're done. So the idea is there's no really expensive materials in there, and that the cost of these things is incredibly cheap to produce. And this is a whole area of organic electronics using molecules as semiconductors. If you take your phone, you've probably all got nice Samsung phones. The screen of those is made of organic molecules, just like this, that emit light. So these are organic electronics, organic molecules in everyday devices. So this is sort of a way of introducing solar cells. An advantage of these organic solar cells, these plastic solar cells, is that they can be fabricated into buildings very, very easily because, of course, they're flexible. So they can be draped over the building, they can be integrated into bags, and they're totally, you can imagine them everywhere. The real advantage with having a sort of plastic flexible material is that when it comes to fabricate them, you don't have to use sort of expensive, well, I'll tell you how you fabricate. When it comes to fabricating, because they're flexible, you can use traditional printing techniques to fabricate them. So I guess you've all seen newspapers being fabricated on a sort of water-wall printing press. And what this means is you print maybe 100 newspapers a minute. And this means you can buy your copy of The Sun for 30p, it's dead cheap. Well, if you replace the paper of your printing press with a plastic substrate, so this plastic here, and you replace the ink of your printing press with a mixture of these two molecules dissolved in a solvent, you can literally print this device just like you print a newspaper. And you can actually inkjet print solar cells like this. And the idea is basically to increase volume, reduce cost. And they're not as efficient as silicon solar cells. It doesn't matter because they're basically as cheap as, well, the idea is they're going to be as cheap as crisp packets to produce.
How efficient are they?
Sorry?
How efficient are they?
Well, you look on the graph. So this is down here. This is down here. So the right at the bottom, they're new. Efficiency per time, they're about 11% efficient. Okay. So it's not the efficiency you should think of. It's like they're 11% efficient, but if they cost nothing to make, you get 11% of the sunlight for free. So it's like it doesn't matter so much about efficiency as long as they're cheap. They're not the issue with MIT. They're not yet cheap and they're not yet reliable. So that's an issue. And there's all types of sort of manufacturing problems with them because because you've got these inks going onto substrates at a very, very high speed, so you get sort of bubbles forming, and fabricating is a very, very difficult process. So now we're going to talk about perovskite solar cells. Now perovskite, I don't know if I've got it wrong. Excuse me. I'm struggling a bit in the middle. Perovskite solar cells on this graph are this brand new line here. So they only started like 2012, so that's when the first one was made. And there's literally been mass hysteria in the scientific community about perovskite solar cells, like literally mass hysteria. And there's ridiculous numbers of papers being published on it. Something like, it's thousands a year. Every chemist is churning out papers on perovskite solar cells. We're all super excited about them. And they started in about 2012 here, and the latest efficiency is about 21%. So let's talk about perovskites. Perovskites aren't actually. Can we go to the next one? Yeah, perovskites aren't actually a new material. They've actually been around for a long time, but not really been used in solar cells before. And they're quite a funky structure. So maybe we'll talk about the structure first. So this is the structure of perovskite material. And it's called, I think, ABX structure. So you've got ions. So you've got some organic ions here. We'll look at that in a minute. You've got halogen ions, so I think like chlorine or something like that. And you've got lead ions here, and that's the formula for perovskite. And the structure looks quite like that. So it's quite distinct from silicon lattices and things like that. Yeah. So the funky thing about perovskites is they're sort of made with this lead and chloride and things like that. But in the middle they've got this organic molecule. So it's a very, very tiny sort of carbon-based molecule. It's quite funky because it sort of spins in the centre and it's sort of semi-free. And the structure of perovskite solar cells looks like this. So you've got this sort of perovskite semiconductor here, and then you've got a couple of contacts. Now, what might be the problem? You might have seen that, but what might be the problem with these perovskite solar cells from that formula? What don't you like about them already? Look at that formula. It's complex. But okay, that's just That's like 30. That's like 40%. Look at the formula. What's in there?
Halogen.
Lead. The Romans all went mad because they had lead pipes. So this is what's wrong with them. They contain lead, which is toxic. They're water soluble. Solar cells are water soluble. Not so good. And also, what's really interesting about the structure is all the molecules of atoms basically move around in them. It's a bit like a jelly, so they're not stable at all. And they've got a very, very short lifetime. So there's mass hysteria about them, and there's lots of people working very hard on them. And you can see the efficiency is really increasing. But when you look at these graphs, this isn't like efficiency for a module. This is like efficiency for a 1 centimetre test cell that's maybe lasted 10 minutes in the lab. So it can be a bit deceiving. Yeah, so there they are. So now I'm going to look at dye-sensitized solar cells. So this is the type of solar cell that lots of research done on and about, well, until perovskites were discovered basically. Once perovskites were discovered, every dumped dye-sensitized solar cells. But I think it's quite interesting to look at them because it sort of shows you the trend in technology and how the community moves on from one thing to another. And yeah. So this is the idea of a dye-sensitized solar cell. The idea is effectively that you've got sort of titanium dioxide here, so like big titanium dioxide structures, and you've got organic dye molecules, so the type of molecules you might find in your paint in your car that absorb light. And basically a photon comes in and excites the dye molecule, and the electron hops away on the titanium dioxide. And this cell is full of sort of iodine mixture, and what happens is the whole, the positive charge, sort of ionizes this iodine, and a sort of charged iodine floats off the contact, loses its charge, and then floats back to the dye. And the big problem with these is, so I've not worked on this at all, so you can probably get a better explanation from Wikipedia. But the advantages are they look pretty. There's a solar cell that's made to look like flowers, etc. But the big problem with them was this sort of this liquid iodine in them. And if you can imagine, so this is maybe, I don't know how thick these were. I think they're like say a micron or something. You imagine trying to keep two sheets of paper effectively a micron apart with a liquid iodine solution in them, and then putting it on a roof and exposing it to sunshine and snow. And at some point they'd probably warp and touch and short out. So as I understand it, the big problem with these was the sort of liquid electrolyte that and it leaks. So, and if you look at the efficiency graph, we'll go back to the efficiency graph. So where's dye-sensitized solar cells? They're in red. So these are dye-sensitized solar cells, and basically they're invented about 1990, and the efficiency basically just stayed flat for years and years and years and years, and not much progress in them until these perovskites were found by the same community, and then they all jumped from this bandwagon onto perovskites. So there's sort of lots of these solar cells and fab technologies, or to some extent. The other type of solar cell is called the cadmium telluride solar cells. And there's been a big scandal recently about cadmium telluride solar cells. There's a company called Hanergy Energy in Hong Kong or China or something. And there's a man that had one company that was producing equipment to make these, as I understand, and selling it to his other company that allegedly made solar cells but didn't. And it had a huge stock price, a little bit like Enron. And what this sort of shows is the solar industry sort of still in its infancy, it's sort of finding its feet, and there's lots of sort of technologies are coming and going, and we haven't sort of got the stable solution yet, or the answer. There's lots of these sort of startups, and these work by basically having this cadmium telluride layer that was the semiconductor, and they had this fairly complicated structure where you had a glass substrate, some type of conductive. The glass is made conductive by putting a metal oxide on it. And then you put your cadmium telluride here, and then you put some metal on the bottom. But you can spot these generally, because if you look at these solar cells, they sort of look deep blue, and they've not got the metallic stripes on them, because they don't need the metallic stripes because of the ITO conducting their electricity. So they look a bit different to the silicon. I think it's too far away. There we go. Now, probably big problem with cadmium telluride is this. So I found this on the internet. I just googled like cadmium data sheet. So let's have a read. hazardous to aquatic environment, acute hazard, hazardous to environment, long-term hazard. And then we've got some skull and crossbones, that looks bad. I don't know what that is, but I'm presuming that's not good, another dead fish. And then if we read this, danger, toxic if swallowed, fatal if inhaled, suspected of causing genetic defects, may cause cancer, suspected of damaging fertility, suspected of damaging the unborn child, causes damage to organs through prolonged or repeated exposure. Very toxic to the aquatic environment, very toxic to aquatic life with long-term lasting effects. I don't know why they've got Danish to the aquatic environment twice, but no point. Don't eat it. So, I mean, would you want that on your solar cell? Not really. So, in my view, it's a failed the lick test, which is, would you lick your solar cell? I wouldn't lick that solar cell. So, I wouldn't probably want to put that on my roof. So, there's all these different technologies. They've got those little ups and downs and positives and negatives. They're very hard, and we're all trying to basically get cheaper than silicon. That's the whole idea. It's a very hard thing to do. Hence, people are looking at all these different, so whatever's interesting in the one people seem to make or haven't been making. Now, multi-junction solar cells. So, these are quite cool. So, do you remember I said before, I don't know if I've got the pictures, that basically if you've got a very high energy photon, like I was just saying, that comes in, and you pop an electron way up into the conduction band, this electron drops down and loses energy. What people have tried to do is try to minimise this energy loss here by making solar cells of material with multiple band gaps. So what you have is firstly material with a very, very big band gap that harvests a very, very high energy light. And then you have material with a smaller band gap that harvests a less high energy light. And then you have sort of material with a much narrower band gap that harvests the sort of much lower energy light. So you've got sort of harvesting of all different kinds of light taking place in specific layers, specifically meant to absorb that light. So you don't get this sort of this loss process that you get in a normal cell. So these are called multi-junction cells. Okay. Now, these are called single-junction cells. Okay. Now, this is the picture of a multi-junction cell, and you can see they're very complicated, and they're also generally made using very expensive processes. They've got multiple layers, and these are microns thick, these layers. It takes a great deal of effort to make these solar cells. But they do absorb very well light here, here, and here to optimize each layer. Now, because it takes so much energy to make these solar cells, what you often do is you get your highly efficient solar cell there, and then you stick a massive lens in front of it and focus the sun energy onto this highly efficient solar cell. So you say, well, it might take me a lot of energy to make this really small solar cell, but if I have a massive lens above it, maybe we win our energy back. And there's some companies that are trying this approach. So here are some solar cells made with lenses to focus the light down into multi-junction cells. And my view is this. I mean, what do I know? My view is it's too complicated and just takes too much energy to make. I might be wrong, but I just think you need a really simple solution, and that's probably not it. Now, concentrated solar cells. So we've got 20 minutes left. I want to do this, and I've got one very short theory section I want to get through, and then we'll finish. So concentrated cells. So the idea of concentrated solar cells is you basically have a massive mirror like this, and it shines energy at effectively a tube like that. And in this tube you might have water, oil, or often salt. And the temperature of these things can get ridiculously hot, like thousands of degrees. So quite often, so this is my excellent drawing of a concentrated solar cell. I think I did this in a hurry at one point. So here's the sun, and it shines its light at a mirror, and this mirror points its energy at some type of tank that heats up. And this gets so hot very often, you don't use water. This is literally rock salt or something you might put in here. And you use this rock salt to basically generate steam and drive a turbine. And I think this is in Spain, there's also one in the US. But literally, you can see this is brilliant white here, and all these mirrors are sort of focus producing a white hot spot on this tower. And you imagine, that's going to be really, really hot. So they're interesting technology. I'm not an expert on them, but I don't know. Yes. Yeah.
So are these PV cells or just mirrors?
Just mirrors. So literally, Sun hits the mirror, hits the and shines it in there. So yeah, there's a few in the world, but there's not loads. So presumably they're not the way to print money. Yeah. Right. So I would like to do some more theory with you. Is that all right? Can you keep awake? Okay. So this is worth doing. So we looked at our. We're going to do this about 10 slides more over. So we have these various diode models. So we have this ideal diode, the diode with a resistor, and the diode with this battery. And you might have noticed that no solar cell or no electrical component you've ever seen in your life has like a rectangular corner there. It's like, you've never seen that ever, because it's totally made up. There's a much better model for a diode. So this is what a real diode looks like. So this is sort of more, if you actually measure this, this is what you'd see. So it's basically the same as this, but what we have is basically an exponential here, as an exponential term. And you can model this as an exponential function. What I said, once we go to negative voltages, we get no current flow. Well, it's not quite true. We'll force through a little bit through your diode, through when it's in negative voltage. And at some point, maybe about 10 volts, you get radon diodes, and you start to get this sort of avalanche current. And you can literally, the diode can no longer hold back the current. And at this point, you know that your diode's failed because it glows red hot. That'll burn you if you touch it. So this is actually smoky at this point. So I thought I'll just teach you about the correct model for this curve, this exponential curve, before I move on to this topic. Oh, this is called I0. This is called like the reverse bias current or the saturation current. Okay. And this is the official equation, or the sort of the equation. I guess you derived this in Eric's lecture.
Or I was trying to.
At least try to. Yeah. Well, we're not going to do that today. Don't worry. I'd really like it. So this is cool. This is basically a very good equation for modelling a diode. You can see it's an exponential function. So this is this exponential here. So that fits this curve much better. Kt is K is the Boltzmann constant. T is temperature, and it's in Kelvin. So room temperature is what 300 Kelvin. So you're putting Kt times T. And N is called the ideality factor that I'm not going to talk to you about, but it's between 1 and 2. And that's it really. And V is the voltage along here. So we can make this equation, or we can add the sunlight to this equation by just adding this extra term, this minus IL for illumination. Okay. So what happens? This is our sort of our exponential function here, and then when we turn the sun on, the diode starts producing current. So we get this negative IL, and just as before, the whole curve just shifts down. Okay. Now, looking at this equation here, so just think about this in your head. Don't shout it out just yet. What will happen as the temperature is increased? What will happen to this curve as the temperature is increased? Just think about it.
Decrease.
Oh, I just said don't shout it. Who was that? Didn't see it. No. That's all right. That wasn't the full answer, but anyway, keep thinking about it. Well, what will happen is that this T will be bigger, right? So to get the same current, you'd have to put on a bigger voltage to compensate for the bigger T. Okay. So what this means is the whole curve gets shifted like this way when you increase the temperature. Okay. So what this means is when it's super cold, when it's snowing, your solar cell is going to be producing a curve out here. When it's super hot, like in the desert, your solar cell shifts to this side and is actually producing less voltage. So the maximum power point we learned is here. So you can see that the power is basically going to be decreasing as you increase the temperature. So what this means is if you've got a nice solar cell on the roof in Bingham, in south of Nottingham or north Nottingham, they'll probably be more efficient at harnessing the sun's energy than solar cells in the Sahara because they're colder. You won't necessarily get more energy out of them, but be more efficient. So you've got to think about it. And even, for example, pushing your solar cells off your roof onto little pegs to make sure there's an air in it can increase the efficiency because it decreases the temperature. So that's a very important thing. So this equation is for sort of the ideal diode, and it's got no resistances in it. Now this is sort of a picture of a solar cell. So here's some silicon, here's some contacts, and here's some front. So this is the back contact, these are some front contacts, and this is a load resistance. Really, when we think, so this equation represents just this diode here, which is just our silicon. We're going to have some contact resistance. We have a little bit of resistance at these contacts here, where we put on metal. We're also going to have a little bit of shunt resistance, which I won't talk about, but there's basically a resistor in parallel with this diode. And if it's from a thin film solar cell, like a organic solar cell, this can come through maybe a contact touch a little bit like that, so that's sort of shorting it out a bit, or maybe have some impurities that sort of short out there a little bit. And a good number for this resistance is about 1 megaohm, and a bad number is about kilogram. And this is usually a couple of ohms. So this is our sort of our solar cell, our improved solar cell model. So we've got some series resistance for this contact, we've got some shunt resistance, whoops, for this sort of resistance here due to maybe impurities or something. And this voltage here is the voltage over this diode only. Okay? So if we wanted to calculate or relate this voltage here to this voltage here, we could just use Kirchhoff's laws, and we could say, for example, well, V over here is V over the shunt is V, so we've got this current plus this current is sort of current here, and then we know the current here, so we could calculate the voltage drop over here, so we can calculate the voltage over this whole circuit. So those of you that have electrical engineers might be able to play that equivalent circuit. How many electrical engineers? Yeah. Okay, so you should be able to relate to voltages here to voltages here. Yeah. So I'd like you to have a go at deriving the non-ideal diode equation. So I'd like you to basically, this voltage here is the voltage between there and there. I'd like you to derive the equation of the voltage between here and here now. And I'll have a go at doing it on the board whilst you do it. And then we'll end. So it seems faster, me or you? So Have you got it yet? That's reassuring. Thank you. So I do have people right. So. Oh, let me put it up. One more time. Yeah, that's almost there. There's one more question. Yeah. Yeah. Oh, what was that? Yeah. I'll go through it. One more time. Please stand up. Okay, I'll take you through it. So here's our circuits, here's our diode, here's our shunt resistance, here's our series resistance. Okay, we know the voltage over this diode here is this V, Okay? We know the current coming out of it is I there. So we know we've got this. So that equation describes the current coming out of here. We know through sort of Kirchhoff's voltage laws that the voltage over here must be the same as the voltage over here. Okay, so we can go V equals IR on that resistor and calculate the current flowing out of this resistor. So we can calculate that, which is voltage over the shunt resistance. Yeah. So we know we've got one current coming in there, one current coming in there. So we've got this current from the diode plus this current from the shunt resistance. So now we've got, I've called this I1 there, which is the current flowing into the diode here. And now we can go V equals IR on this resistor here to calculate the voltage drop over there. So we go R series times I1. So this is I1 times R, and that's the voltage drop over there. Is that times the voltage, or plus the voltage over here. So this element plus this element equals the total voltage out of there. Okay? Yes?
In the current, you disregarded the current due to lighting, IL.
Ah!
Okay.
What was it called? IL. Yeah. Happy?
Yeah.
Okay. So just have a go at that. I think that is the end of the lecture. Ah, no, one more slide, sorry. So when you plot the dark curve of a diode, you get on a log scale, so this is a log scale, you get a curve that looks like this. And this section here is due to this resistance here. Okay, that's due to this shunt resistance. And if this goes up a lot, you've got lots of dark currents, you've got a bad solar cell. And if this goes down, it's a very good solar cell. And this is basically the diode turning on. So this is this sort of exponential part. So that's this exponential turn on. And this part here, the diode's fully turned on. And this is just basically the series resistance. So this is the series resistance here is influencing this part of the dark cell. And I'm not going to go into it much, you can look in that book, but basically if you've got a solar cell dark JV curve and you plot it on a log scale, you can learn loads about solar cell as well worth doing. That's it. Any questions? Yes?
So the efficiency or the voltage created from a PV cell decreases with the temperature?
Yes.
The temperature increases. So before you showed the picture of a solar cell with those concentrating lenses on it.
Yes.
So wouldn't that make the PV cell less efficient?
Yes. So actually, you can get those concentrator things can go up to like a. I mean, the ones I showed in that picture that were actually the. We've got 100 slides.
Alright. Don't pack up just yet. Yeah, so these ones here, you can actually get hugely hot devices. The devices can get really, really hot. And you know, the thing of that might be a 10 sun. So you also need a heat sink to try and keep the temperature down. Yeah, please don't pack up. Let's just talk about, because this is always the most important part of the lecture.
Please tell us about the shape of the solar cell. Why the shape of the solar cell like that?
Why they're square?
Yeah.
That's quite a good question, actually.
Is there any appropriate shape for high CNC or something?
I'll tell you about the shape first. So the shape, you can see this square here, like that, is basically determined by the size of this rod. And this thing is made by sort of low, on the next one again, it's sort of made by pulling out of a solution, sort of liquid silicon. So this thing sort of, you see sort of, it's a bit like it's come out of the liquid. That takes the shape. And I think, I'm not totally sure they've got, I imagine they've got these cut-off edges because it's round, it's kind of a round thing. And as for the most efficient shape, I don't think it's the most efficient shape, but people put a lot of effort into optimising the thickness. Because obviously if it's super thick, it will absorb all the light. It'll take a long time for electrons and holes to get from one contact to the other. So they might recombine and get lost, so the efficiency goes down. Whereas if you make it super thin, all electrons and holes will get out, but
but it won't absorb much light. So there's always this play-off in terms of thickness. Yeah. Any others? Any others? Okay. All right. So